Hi, I'm Ned, and I make games. Today I'm returning to grass rendering by showcasing another style of grass made using Unity's Universal Render Pipeline. This technique uses a compute shader to model little blades of grass, which bend and wave with the wind. I recommend you watch my video on compute shaders to make sure you're up to speed. I'll put a link in the corner and the video description. This is also the fourth in a series on grass rendering. You don't have to watch the previous videos, but they might give you some insight into the process. I made this project using Unity 2020.1.16 F1 and Universal Render Pipeline 8.3.1. If you're using a different version, check the comments for updates. To get started, enable the Universal Render Pipeline by downloading the package, creating a settings asset, and enabling it in your project. Then, open a 3D modeling program and create a flat plane to generate grass on. A blade will sprout from the center of each triangle in the mesh. You could use Unity's default plane, but the grass looks better on a mesh that's more dense. Once you're done, create a new compute shader in Unity called Grass Blades Compute. Then, download the NMG Grass Blades Compute Helpers.hlsl file from the video description. It contains some math and helper functions we'll be using. You'll have to create the HLSL file in your operating system. Open the compute shader. Let's start out by drawing a green triangle on top of each triangle in the source mesh. Define a kernel called main and include the helper function file. Now, let's take a look at the data structures. They should be familiar from the compute shader video. From the source mesh, we only need the object space position. These two buffers contain the vertices and triangles of the source mesh, arranged as triplets of indices into the vertex array. This drawVertex struct defines the output vertices. They contain the position in world space, as well as height, used to interpolate the blade color. The draw triangle will contain 3 points, as well as a normal to use for lighting. This normal will actually point parallel to the grass blade. Since grass is semi-translucent, using this normal for lighting gives a more natural look for the final product. Finally, create an append buffer to use as a stack for the output triangles. As opposed to the previous grass renderer, this time we'll use the indirect arguments buffer in this shader. As a refresher, the graphics engine reads the values inside this buffer to know how many vertices are in the computed mesh to draw. We'll count vertices manually in the kernel function, allowing us to skip the triangle count to vertex count compute shader used in the last video. The argument buffer must be read and write enabled, so we can modify it in the shader. Next, we'll receive some variables from the C# renderer script, including the number of source triangles and a local to world transformation matrix. Let's move on to the kernel function. Set the number of threads to 128.1.1. Again, we'll use the X component of the thread ID to process the source triangles. Inside the function, return if the ID is larger than the number of source triangles. Now, we need to compute the center of the triangle and a few other vectors. Let's define a function to help position our blade in the world. Using the 3 triangle corners, it will find the center point and the normal of the triangle. First, convert each vertex position to world space. Then, calculate the center position from that. This next function will calculate a triangle's normal, as well as something called a tangent space to world space transformation matrix. You may be wondering, what is tangent space? It's a coordinate system based around a surface. In tangent space, the z-coordinate points along the surface's normal. Then the x-coordinate points parallel or tangent to the surface. When working with UVs, the x-component usually points in the same direction as the u-coordinate. Since we're working with a triangle, let's have it point from the first to the second triangle corner. Finally, the y-coordinate points perpendicular to both the x and z vectors, along a direction called the bitangent. Now that we have defined a tangent basis, we can construct a matrix to convert from tangent space to world space. All we have to do is multiply a point with the matrix to do that. This will be very useful. It's simpler to construct our grass blade in tangent space. For instance, the corners of the grass triangle will be at -1/2, 0, 0, 1/2, 0, 0, and 0, 0, 1. So, back to the script, this function will calculate all of that for us. It's in the helper function file if you're curious to see how it works. Returning to the kernel, call this new function, passing in the triangle corners, then create an array of draw vertex to hold the points of the draw triangle. Now, we can call the setUpBladePoint function, passing it the blade's anchor point, the tangent to world matrix, and the UV of each vertex. Inside, we can easily convert the UV to tangent space, and then convert that to world space. Also, set a height, again for color blending. Then construct the triangle from the points array and append it to the buffer. Don't forget to set the lighting normal. Now we need to add 3 to the vertex count in the indirect arguments buffer. We can't just use the normal addition operator, since this kernel function is multi-threaded. Doing so would introduce some race conditions, leading to unpredictable errors. This interlocked add function makes sure that only one thread at a time adds to the buffer. Now, return to Unity and create the graphic shader, an unlit shader called GrassBlades. Also, create a grassblades.hlsl file and an nmg grassblades graphics helpers.hlsl file. This file is also found in the video description. Once again, you'll have to create the HLSL files in your operating system. In the shader file, rename the shader and remove the default properties. Replace them with a base color and a tip color. In the subshader tags, add Universal Pipeline. In the pass, remove the boilerplate code, add in the light mode tag, and turn off culling. These grass blades will not have any thickness, and they'll need to be visible from both sides. Then add the platform requirement pragmas, the light and shadow keyword pragmas, the function registry pragmas, the hash include grassblades.hlsl file. Okay, open that HLSL file. At the top, add a hashif block to stop the file from being loaded twice, and then add a couple of include lines to import the helper functions and the URP lighting functions. For the data structs, you can copy and paste the draw vertex and triangle from the compute shader. The append buffer becomes a structured buffer here, so we can read it like an array. Next is a fairly standard vertex output structure with a single UV for blending colors, a position, normal, and clip space position. Then, define variables for the material colors. The rest of the shader is also pretty simple. The vertex function needs to get the triangle and vertex that correspond to the vertex ID passed to it. Then, set the position, normal, UV, and clip space position in the output structure. The fragment function is very standard. It calculates data for the lighting algorithm, figures out the albedo by blending the base and tip colors with the UV, and calls the URP lighting function to calculate the final color. Return to the scene editor and create a material for your shader. There's still one more script to write until we can see anything. Create a C# script called the procedural grass renderer. Open that up, add serialized fields for the source mesh, compute buffer, and material. Then create a structure for the source mesh data, only containing a position. Define several instance variables, including an initialized state variable, the 4 buffers, source vertex, source triangle, draw, and indirect argument, the ID of the grass kernel, the grass kernel dispatch size, and the bounds of the mesh and local space. Next, calculate the strides for each compute buffer. The draw buffer contains 3 floats on the triangle for the normal vector, plus 4 floats per vertex for position and height. Now, this array will hold the initialized data for the indirect buffer. We have to reset the buffer to this at the beginning of each frame. In onEnable, add some assertions to make sure settings aren't null before the script runs. Then, make sure things are cleaned up if the script hasn't been initialized. Gather data from the source mesh and compile the data to upload to the vertex and triangle buffers. Then, calculate the number of source triangles. Initialize the various buffers. Make sure the draw buffer is an append type, so the compute shader can add to it on the fly. For each source triangle, we'll output one draw triangle, so the length of the draw buffer is the source triangle count, for now anyway. Now, get the ID of the grass kernel, set some variables on the compute shader and the material, then calculate the dispatch size, so it will cover all source triangles, and make a rough estimation of the local bounds. In the onDisable function, release all buffers. In late update, reset the system if it's in edit mode, then clear the draw buffer, Reset the indirect arguments buffer so the compute shader can count vertices starting from 0. Then transform the bounds to global space, upload the local to world matrix, dispatch the grass kernel, and call drawIndirectProcedural to trigger the graphic shader. Finally, return to the scene editor and create a game object. Add the procedural grass renderer component to it, and fill in all fields accordingly. You might have to enter play mode first before you can see anything. But there we go, some green triangles. There's a lot to do before they look like grass. Let's first make them more customizable and randomized. Open the compute shader file and add a few float properties: height, height variance, width, width variance, and max bend angle. The variance fields describe the amount each dimension will vary between blades, while the max bend angle describes the amount the grass blades could lean forward, as if bending under their weight. Write this getBladeDimensions function to add in height and width variance. It generates two random numbers based on world position, and then adjusts the width and height with them. So all blades don't face the same way, I want to rotate each around the tangent z-axis by a random angle. We can do this by calculating another transformation matrix. This angle axis 3x3 function generates a rotation matrix that rotates around the given axis by the given angle. Pass it an up vector and a random angle to create the matrix we need. Now, to handle the bend, we want a similar matrix to rotate the blade towards the ground, or along the tangent space x-axis. The angle should be random too, but bounded by the max bend property multiplied by 90 degrees. Apply these rotations by multiplying them with a tangent to world rotation. Remember, matrix rotations are applied in reverse order of multiplication. Since the twist and bend rotations are in tangent space, they must apply before converting to world space. Accordingly, they must appear last in the multiplication chain. Pass the new dimensions and transform to set up blade point. Don't forget to update the argument list, and multiply the offsets by the dimensions. In the renderer script, create a grass settings serializable object, and add variables for max bend angle, height, width, and height and width variance. Add a serialized field for the setting object. In onEnable, pass those settings to the shader, then multiply the bounds by the maximum size of a blade. Return to Unity and test it out. It's looking better already. The next step is to add curvature and detail to the blades by adding more triangles to each blade. I'll do this by breaking the blade into multiple segments, with an edge between them. In the compute shader, we need to set a maximum number of supported segments, and the corresponding maximum number of points. There are 2 points per segment, plus the tip point. So this formula calculates the number of points correctly. This line also defines the length of the point array in the kernel function. Next, add a couple of variables to set the number of segments to generate, as well as a curvature variable to fine-tune the shape. In the kernel function, bound the number of segments by the maximum supported amount. Let's generate the points in a loop now, creating the bottom edge of each segment. Since these segments are just subdividing the grass triangle we created before, we can calculate the UV of these points linearly. The v-coordinate climbs the blade as we progress in the loop, but it never reaches 0, while the u-coordinate converges on 1/2. Since we want the blade to have a natural-looking curve, we need to increase the bend angle as we progress up the blade. To do that, we can modify the transform matrix based on the height. Write this function to do it. Pass in the twist and tangent to world matrices, since they are constant per blade, as well as the bend angle. Then, in the function, calculate the bend matrix. To have the blade bend more towards the top, use a power function with the curvature property. Multiply the various transformations together just like before. Now we have everything needed to create the bottom 2 vertices of this segment. Pass the position, dimensions, transformation matrix, and UV to the setup function. Note, the U of the second blade is subtracted from 1, creating 2 symmetrical points. Now we need to calculate the tip vertex. Call the transform function with a height of 1, and then call setup blade point, adding the result to the list. So we have a list of vertices, but we need to transform that into triangles. Let's first count the number of triangles, 1 in the tip segment, and then 2 in each other segment. Notice how we've laid out the points in the array? We can create the triangles from every 3 consecutive points. It's as simple as writing a loop to iterate through the point array, creating each triangle structure and appending it to the buffer. Don't forget to adjust the vertex count to account for more triangles here. In the C# renderer, add grass settings for the max segments and blade curvature. In onEnable, ensure the max segments is always at least 1, and then calculate how many triangles are in each blade, just like we did in the compute shader. Now update the draw buffer size according to this new number of triangles, and then pass the new settings to the shader. Back in Unity, test out the curvature and see how it affects your grass. It's looking pretty good. Now let's breathe life into it with wind. Just like in the other grass renderers, I'll simulate wind using a noise texture. Again, we'll need the red and green channels, so make sure to generate independent noise in each. In the texture importer, set sRGB to off and turn off compression. Then open the compute shader. Thanks to the core.hls file included here, we can reference textures just like we would in a graphics shader. Do that, and then add variables for texture scale, wind frequency, wind position multiplier, and wind offset amplitude. We'll implement wind using another rotation matrix. We'll have the noise texture generate the rotation axis, but first we need the texture UVs. It should vary by the X and Z world position and time, scaling each by their respective properties, and then adding them together. Apply the wind texture scale next. Sample the texture with this UV, and then use the red and green channels as the X and Z coordinates of a world space vector. Taking the cross product of that vector with the grass's normal, will produce a rotation axis that's consistent across blades, but also perpendicular to the blade's growth direction. In the kernel function, call getWindAxis before the loop. Points closer to the tip should feel the wind more, so we'll pass the wind axis to the figure transformation for height function in both instances it appears. Compute the wind direction matrix using the wind axis and the wind amplitude angle, scaled by the height on the blade. Since the wind axis is in world space, we need to apply it when the rotation is also in world space. In other words, it must be applied after the tangent to world rotation. Remember, rotations are applied in the opposite order of multiplication, so the wind matrix should appear first in the chain. Okay, we're done here for now, so open the C# renderer. Add settings for each wind variable and, in onEnable, pass them all to the grass compute shader. We also need to manually set the _time variable, since Unity does not automatically do so for compute shaders. Update it in late update. To maintain consistency, put the time value in the Y component. Return to the scene editor and define the wind settings. You may need to enter play mode to see any movement. Alright, that's looking good. I think we should make a field of grass with this stuff. Unfortunately, if you duplicate the renderer, you encounter the problem with game objects sharing a compute shader. The second renderer overwrites the compute buffer in the first, preventing it from rendering. To fix this, open the C# renderer script, and add fields to hold instantiated copies of the compute shader and material. In onEnable, instantiate each, and replace all references with the instantiated versions. In onDisable, destroy the copied shaders. In late update, update the references to refer to the copies. Now, returning to Unity, you can see a lot more grass. Now, if you tried to test this with a bunch of different grass renderers, you'd quickly kill your FPS. One way to help with this is with LOD or level of detail calculations. This technique simplifies blades that are far from the camera, outside of the player's notice. We'll do this by decreasing the number of blade segments for faraway blades. Open the compute shader and create variables for the LOD settings. To organize things, I'll put them all into a single vector, where the X component is the smallest distance from the camera, where LOD will start to take effect. The Y component is the distance from the camera, where blades will be their most simple, and the Z component is a curvature factor affecting the transition between these two states. Create a getNumSegments function which takes in world space position. We'll calculate the number of segments to generate here. Calculate the distance from the camera, then unlerp that to receive 1 at the minimum distance and 0 at the maximum. Apply the curvature factor and multiply with the maximum number of segments. Clamp this number so we get sensible results, then return. In the kernel function, call getNumSegments here. In the C# renderer, add fields for the LOD settings in the grass settings variable, and pass them to the compute shader in onEnable. Then, in late update, pass the shader the position of the camera. Return to Unity and fine-tune these LOD settings. To create a large field, turn your grass into a prefab and copy it all over the place. If you get the settings right, you'll never be able to tell where the LOD takes effect. And that's it. You've created some remarkable looking grass, if I say so myself. Now, we've created 3 different styles of grass using a variety of rendering techniques, so you'd think we'd be done with this series. But rendering grass is a very deep rabbit hole to dive into, and I'm afraid we've only just scratched the surface. In a future video, I'll detail how to make your grass react to creatures trampling it. So please subscribe and turn on notifications so you won't miss it. Thanks so much for watching. I'd really appreciate it if you could like this video. It lets YouTube know to recommend it, and it really helps out the channel. Of course, please leave a comment if you have any questions. I have one for you. How do you plan to use grass in your project? Do you have a topic you'd like to see me cover? Thanks again for watching, and make games.